Okay, sorry, technical difficulties. So all I'm doing today is reviewing for the final exam. The final exam is on Tuesday in here at 9, I believe. You can find out just by Googling Weaver final exam schedule, and it'll pop up with this rubric that lists based on like class time and day what it is. I'll send out an announcement, I'll verify, but I'm pretty sure it's Tuesday at 9.
What, 9 to 11?
10:50, yeah. So 2 hours and 50-minute exam, so it's 10 minutes between. We will meet here. Again, you can take it remotely. I strongly recommend coming. It does, everyone has done better for it. I don't know, this exam is gonna be kind of hard just because it will cover the whole semester. Now it'll focus on state machines, and it will definitely have questions about the project that you guys have been working on. Hopefully no one has because you can, I don't know, I haven't checked. You can probably go find code for similar or the same thing, maybe from past years. If you just copied and stolen code from the microprocessor, you're gonna bomb the exam, and I'm gonna run it through it, turn it in, check, and you'll get 0 and blah, blah, blah. So don't cheat on the microprocessor. Make sure you use office hours. It's going to be on the exam in some form or another. I'll give an example here. I'm actually going to go through my final exam from last semester. So you'll have a pretty good representation of what the exam will look like. And then maybe a few other things. So it's not going to be comprehensive because anything that was lab, homework, or exam or project from earlier this semester is valid for the final. So the way I did the final last time is I started off with some easy ones that should just be 3 points, being that, so the first question was convert the following decimal numbers to 8-bit binary. Okay, so I did something like 59. So this is going to be open notes, open book, open internet, right? So the first thing that you could do is just type in binary or decimal to binary conversion, right? Type it in. If I say you have to show your work on this one, all you have to do, right, is remember that, well, it's 8 bits, 3, 4, 5, 6, 7, 8, and they go up in powers of 2, right? It's 2 to the n, and 2 to the 0 is 1, 4, 8, 16, 32, 64, 128. And then the easy way to figure out 59 is start by what is the biggest number I can add without going over, right? It's 32. And then we're just adding all of these columns together. So 32 plus 16 is 48, still less than 59, so I add it. And I go find the next biggest one. So 32 plus 16, 48 plus 8 is 56, right? So we're still under. This would be 60, so we'd be over. That's over, right? Or sorry, that's. Anyways, you just start adding. If you're not tired, hopefully adding is easier. So I guess get better sleep than I did before the exam. And then add the 2 zeros because it says 8-bit binary. You'll miss some points if you don't have 8 bits in it. That's all the conversion is going to be. Of course, you can Google it, get the number, and then draw this. That's all I ask. If I say show your work, that's all I ask. Even if you use Google to get it, maybe I need to show you that. Show me that you understand. I could do the same type of thing with 2's complement numbers, right? So here's, if I say, here is this 4-bit 2's complement number, what is it in decimal? Remember? Yeah, so we know that the first bit in 2's complement is negative, and it's negative the value that it's at, right? So here where we have 1, 2, 4, 8, the biggest bit is -8, right? Which is different than signed and unsigned. Right? Because if I just say, give me a, what is this as a signed number? It's -101, right? As opposed to 2's complement, which is -8 plus 4 plus 1. Keep those straight, because something like that could show up. I could do something simple like give me the truth table for this device. Give me the truth table for this device. Or so on and so forth. Or I could even do it a little more complicated. I don't even know what this truth table ends up looking like. I'm just making something up. Give me the truth table for this circuit. Right? Something like that. It's going to have devices, have truth tables, just way back to the beginning semester. Hopefully this stuff is brain dead work for you. Next question. Okay, so this next one is jumping a little bit ahead in difficulty. And it's going to be a question about static hazards, right? So that's some of the newer material. So something about static hazards will be on the final, I promise that. It's going to ask, so it's a 4-part question. Part A asks, what is an indicator that there is likely a static hazard that you can see just by looking at the K-map with the implicants circled? So how does a K-map warn us that maybe that there's likely a static hazard? Yes, adjacent ones that don't share an implicant. Right, because, and I have to specify in that question that the implicants are circled, because if they're not circled, then I could have this orange circle, right? Now there's no risk for a static hazard. Okay, so that's testing that principle of, is there a static hazard? Well, I just answered it. Part B, how would you prevent a static hazard in that K-map? You would have a circle, right? You would make sure that there are no 2 adjacent ones unless they share an implicant. So we just add it. Part C, if the signal you suspect of creating a static hazard passes through a 3-input AND gate, what would you do to each of the signals to prime the circuit? So remember this idea of priming the circuit? Right, so I have an AND gate. And I have a signal A. I'm interested in A. Let's say that A is my signal that I'm worried about having a hazard on. There's some other circuit that A is connected to, blah, blah. But let's just worry about this AND gate. What do I do with signals B and C to prime the circuit? I set them both to 1. Because if they're 1, the output of this AND gate can react to A changing. If either of them are 0, A cannot react. Or A cannot trigger this gate to react. Therefore, it's not primed. It's not ready to respond to my signal of concern. Okay. And then part D, this was what I would call a well-written question because A, B, C are all related, but they are not dependent upon each other. And then D brings in the hard part. Okay, given this circuit, which of these signals is at risk? Actually, I'll call this Z real quick. Which of these signals is at risk for having a static hazard? C. Why? Yes, it has two different paths. There's one path that's 1, 2, 3 gates, and one path that is 2 gates. The signal that has two differing path lengths is at risk for a static hazard. Now, I won't, but I could. I just want you to understand that it could be different, right? Because like a NOR gate has a longer delay than an OR gate. It just does because it takes more gates to make that, more transistors. I'm going to be easy on you and say they're all 10 nano, most likely, something like that. They're all the same. But be aware that you could have two paths that have different number of gates, but have the same delay or something weird. I'm not going to do that, but it could happen. Okay, make sure I can get all of this in the window. So that means that C is our risk. So I'm going to write C at the bottom just for that. What do I do? What do I do to A, B, and D in order to prime them, right? That's the first thing that we have to do is I have to prime the circuit to react to the hazard. Yeah, so A is high because it's an AND gate, right? That's how I prime it. So A is 1, oops, sorry, I was correct, 1 forever. B is going into an OR gate. How do I prime an OR gate? 0, right? Because if it's 1, no matter what C does, it doesn't change. So therefore, prime it with 0 forever. B, NOR gate. Well, unsurprisingly, you can find out through the truth table. So if I have A, B inputs, I have OR, NOR, OR is, right? That's OR, NOR is just not that. Okay. So let's say I want to, well, let's call it what it is instead of A and B and call it C and D. Okay, if I want this circuit to react to a change in C, what does D have to be? Well, D here, if D is 0, then C changes. If D is 1, no matter what C does, the output 0. Right? So that's how you find out what prime is. Okay, so therefore we just go ahead and look and say, well, it turns out that we need D to be 0, which is the same as an OR gate, which makes sense, right? Because if you consider your NOR gate as that, of course it's the same, right? The NOR changes nothing because I need this node to change and the inverter doesn't care. That's all a NOR gate is. So it stays the same. So we prime it the same way as an OR gate, therefore D is 0. Okay. Now, C is what changes. And I know that it has to be a static 1 or static 0 hazard, right? Which means it's either supposed to stay at 1 and it doesn't, or it's supposed to stay at 0 and it doesn't, right? Well, it turns out that it's easier for me to write static 1 circuits than static 0 hazard circuits. But regardless, all you have to do is really find out, you have to prime the circuit and find out what is Z. Well, we have to pick something for C. So let's go with C going from 0 to 1. And then I'm going to give it enough space so that the circuit can resolve before I go from 1 back to 0. Right? Because it's going to happen one way or the other. Either it's going to trigger going from 0 to 1 or 1 to 0. So if I do both, I'll find the hazard. Okay. So how long it's going to take? There's 3 gate delays. If I call each one of these 10 nanoseconds, which I can, I want to just make sure there's time to settle. 10, 20, 30, 40. Okay, so if it's 3 gates, I need at least 1, 2, 3, and I'm going to call it 4 before I change. Right, just so that there's enough time for it to resolve the full delay path. And then we'll stay here. And now I have my 0 to 1 transition and my 1 to 0 transition. And we could just start by finding if there's a glitch. Start by labeling the nodes, E and F, and finding out what they do. Right? This is just like any timing diagram problem. It's just this one has a delay in it. And as long as you do it right, the answer will come out. Right? Okay. So E. E is just A and B or C. So maybe I should come in here first and call something alpha. Okay, so if this is alpha, I need B or C. Well, B is 0, so it's just C, right? It just mirrors C with 10 nanoseconds of delay. Right, because there's a gate, so there's a delay. Okay, now I can look at E much easier because it's alpha and A. But A is prime, so A is always 1, so it's just alpha with the delay. Right? I didn't have to worry that the cause of this change is C. I just worried that the input alpha changed. So as long as I do this one node at a time and keep it clear and don't ruin my delays, I'll be okay. All right. F. Well, F is C nor D. But D is 0, right? So it's prime, so it only reacts to C, and it's just not C. Does everyone see that? Okay, so if it's not C with a 10 nanosecond delay. So we start high, it raises to 1, so we drop low with the 10 nanoseconds. And we come over to here, this is the change, 10 nanoseconds. Sorry, I've got a little bit of a tilt in my brain apparently, because everything's kind of dropping. Okay. Z. Now that I have E and F, I can worry about Z. Z is just E or F. I don't have to worry about any other signals as long as I've done those 2 right. Well, here at F, I'm at 1, right? Because of F, Z is 1. It stays 1 here. It drops to 0. And it's also 0 here. There is a gate delay, however, so it stays 1 because this time X is pushed to there. So that means time Y is pushed to there, right? Because of that delay. So that when we're high, this drops low, it drops low here. And now E takes over. And so it raises back to 1. And then it stays 1 until we go back to that other transition. That's my hazard. right? Because it was supposed to be 1. Whether C is 0 or 1 doesn't matter. For this prime circuit, if C is 0 or C is 1, the output is supposed to be 1. It's not, because of that transition, because of that hazard.
The toggle C faster, would that just make the glitch harder to see, or would that create more?
It makes it difficult to see. Because so the issue is that you're still going to have the hazard, but the delay path can do really weird things because it takes longer. This one could still be correct as this one is wrong, and so it ends up overlapping and disguising the hazard. So I would just find the major delay path and do 1 segment longer than that so that you have a guaranteed settling time. All that means really is worst case. I mean, this is as long as it's really going to be. It won't be much longer than twice this, just by nature. Unless I mean, I have a really big circuit to make worse than that. I could do simple things, right? I could add inverters. I could throw in other types of gates, NAND gates, and so on. But that's the general principle. There will be a question like this. You want to get good at comfortable with that kind of question because you want to go fast. Okay, that's static hazard.
I have a question.
Yeah.
So we found a static hazard because Z was 0 and was supposed to be 1 the whole time.
Yes.
How did you know that it was supposed to be 1?
That answer is actually pretty straightforward. It's because I can't prime, it's difficult to prime the circuit to be 0. The circuit I can't prime to be 0 in response to this C. Right? Because any other way I prime this circuit, the C changing doesn't matter. And so in order to find the static 0, you actually wouldn't even know the difference until you did it. Now it's a static 0 hazard. Right? And that's all. So prime the circuit, figure out what it is, right? And you can double check. There's only one signal that is a potential hazard, right? And the way it's a hazard is that independent of what its value is, the output is the same. So if I solve the circuit for what is Z when C is 0, and what is Z for when C is 1, well, it's 1. Until now, it's 0. Oh, for the people in the video.
Okay, so if you prime it correctly, then Z should stay the same the whole time.
Yeah.
And when it changes, that's how you prime it.
Yeah. Yeah. And I could even ask more simply, right? Because if C is the only one with a differing delay path and the output changes, when C changes, it's not the same, right? There's no risk for static hazard there. That's where dynamic hazards come into play, but we're not talking about those, right? I've left that for next semester. Well, whenever you take 3610. Okay, what do I got next? Oh yeah, this is a flashback to the early labs. This one says dry circuit that uses an LED, a resistor, the power supplies, and a digital signal that causes an LED to turn on when the digital signal is asserted high. Okay, that's just right. So I'm saying I need something like a resistor. I need an LED. I need the power supplies, maybe. And digital signal, right, which is just the input, DS. Okay. Build a circuit using these bits that turns the LED on when the digital signal is high. Okay, well, we take a resistor. Point of this resistor, right, is just to limit the current so we don't blow up our LEDs. It goes through an LED. And it turns out I don't need VCC rail, I just need the ground rail. And digital signal comes in here. Done, right? If this is a 1, we get the voltage drop, it flows through. If it's a 0, it goes ground to ground, nothing happens. If I draw the signal wrong, it doesn't turn on, right? I could do things like I could throw in switches, ask you to use those, say the switch is turned on via some, like, even say like a digital signal controls this switch. I could ask it in relation to the breadboard. Right, this is all stuff from those first 3 labs or so. It's fair game, it could be asked. It's easy now, I hope. Is anyone here not in 1270 or not taken 1270? All of you? Oh, you haven't yet. Okay, so you might have the most difficult because everyone else has had more practice with this, but all right, next question. Like some of these are just supposed to be giving points. It's just making sure that you paid attention and studied a little bit. This is a microprocessor question. I can almost guarantee you that the microprocessor question I give you will be more difficult than this one. It says, in the project, you designed a microprocessor. For each of the blocks listed below, write C if it's combinational and S if it's sequential. Combinational logic, sequential logic. Okay, so we have an ALU. We have an accumulator. We have the memory interface. And we have the controller. That's what I listed. Are they combinational or sequential? What is the ALU? What's the difference? What is the difference between combinational and sequential logic?
Is the clock right?
It's clocked and it has memory. It remembers what happened before. Does the ALU remember what happened before? No, it doesn't. Therefore, combinational. Does the accumulator remember?
Yes.
Yes, that's its whole purpose. It's the memory part for the accumulator. Sequential. The memory interface. Combinational or sequential? It's combinational. Remember, because all it is a mux and a buffer. That's all. There's no clock there. Combination. Controller. Sequential. Everyone should get that one, right? And you can almost, yeah, anyways. This type of question is likely to be on there, something that asks about combinational and sequential circuits. But your microprocessor question will be more like another one that's upcoming. Again, this one actually has 2 microprocessor questions because the project is important. Okay, we'll come back to that though when we get there, and we'll go on to the next one. And this one is just call back to K-maps. It says, consider the truth table on the right, which I'm going to do on the left first. F, A, B, C, D. I'm not going to write out all of the numbers. I'll just write enough to remind you what's happening. And then it does this. Consider this truth table. Use the provided K-map, which I put one out for you guys. It looks like this. And that's where I stopped. And I said, use the provided K-map to provide a minimum sum of products expression. Okay, and you're going to go ahead and fill this in. The first thing that you're going to want to do, right, is make sure that you remember these. I didn't grade based on this, but literally every person last semester that didn't write out the numbers got the columns and wrong. Either the column or the row. They screwed up one or the other. Every single person that didn't write it down did it. And then we just fill it out, right? And the way I like to do it is to make sure I'm not crazy is 0, 0, 0, 0 is always here. And it's a 1 in this case. And then I just find where this next one is based on the order of the inputs. So it's 0, 0, 0, 1 for A, B, C, D. So 0, 0, 0, 1 is that one. Now I know the direction this K-map is going. It's super quick to fill in the rest as long as I don't screw up any rows. This one is actually really a nice K-map on accident. So 1, 1, 1, 1, 0, 0, 0, 0. There's 4 zeros. 1, 0, 1, 1, 1, 0, 1, 1. Oh no, I flipped it. Well, it turns out that it's the same.
The fourth row or fourth column.
It should. That's what I was saying though, is it's accidentally the same. This example that I pulled. This is like the easiest possible K-map. I ended up not using this one because of this when I did my exam, I think. And there's one other K-map question here too. I don't think I'll do two for you guys. But it was just, right, the other question I get asked is do a product of sums. Yeah, it's just the zeros and you flip the inputs. Remember that part, because a lot of people forget that. So like this is not A, B, it's A, not B. And it's A. Say that louder?
Sorry, you get it right, and then you could just put thing over it all.
Yeah, you could do that. And you could do the A and B or the A or, right, it's just a Morgan's, which you guys remember, which says something like this. We'll start with the and just to make sense. A and B, De Morgan's, this flips and these flip. Anyway, that's De Morgan's. There could be a question on De Morgan's, so I'm glad you brought that up. Other than that, we circle the ones. For the minimum expression, I think there's only one valid way. Some of these have multiple ways to do a minimum expression that are equally valid. This one only has one, I believe. And then you use those to write the expression. I'm not going to do that so we don't run out of time on this review. Part B says, draw the circuit using inverters, AND gates, and OR gates. Well, we just take this and we say, we know that there's 1, 2, 3, 2 input AND gates. There's an OR gate. Each of these has 2 inputs. We can figure out what they are. The fact that it says use inverters, not you may use inverters, it says use inverters, AND gates, and OR gates, means that if I have something like this, which is not A, not B, maybe inverters. The other way I could specify that, and I could say something like, assume that you only have access to the active high inputs. Right? So that's saying that you only have A or B. A, B, and C. Not the other way that you might be tempted to write it would be C not, right? And then just plug C bar into there. You don't have access to that. You have KVs. Okay. And then the next question is convert it to strictly NAND gates. Okay, you read it on the circuit and we do the bubble pushing, right? That's all I'm going to ask of you. Put a bubble there, put a bubble there, right? That's equivalent to putting 2 bubbles there and pushing it back along. Not is the same as staying the same as a buffer, right? So that's all that's doing. Repeat with the other 2. This is one way to write a NAND gate. This is another way to write a NAND gate. Remember the same thing for NOR gates if you do the product of sums. Then the last thing, don't forget to do, I said NAND gates only. You could just draw the inverters and do something like this. How do I make an inverter out of a NAND gate? An inverter. Then I can just draw this and point an arrow. Okay. Then I ask, write a combinational VHDL expression for this circuit. There's 2 different ways to do this that are okay. One of them is the NAND gate circuit, and one of them is the AND and OR gate circuit. I didn't specify which circuit when I asked for it, so either one would be correct. If you were to do that, combinational VHDL means no process, right? It's just an assignment statement. It's as easy as, and a surprisingly large number of students miss this. It's just as easy as writing, what do I want to do this? If the output is called F, I say F gets assigned to this kind of equal. Well, I'm not going to go through it, but I know the first one is not A and not B. Right. That's all the combinational expression is. Remember to keep track of that. That's all it is. Make sure you can write VHDL and remember the semicolon. Okay. This one I'm going to switch over. Oh, I'm going to skip one question and come back to it. Okay, so this one should be really easy for you guys after what you did on the last exam, and you all did really well. Clock, J, K, Q. Forward, okay. Okay. Question says, finish the timing diagram for this JK flip-flop. Assume that it has no clock to Q delay. Okay. The first step of this is making sure we know what a JK flip-flop does. JK flip-flop being different than a JK latch reaction, right? And the other clue would be there would be no clock in a JK latch. Doesn't make sense. Okay, so JK, and I could ask you to draw a table like this. I said, draw me, part of the question could be, write the truth table for the JK flip-flop. So remembering the notation, if we're 0, 0, we're Qn plus 1. For 1, 1, we're just Qn. Wait, no, sorry, not Qn plus 1. We're Qn and Qn bar. There we go. Right. That toggles, that holds. And this one counts up. Okay, so that means just K is reset and just J is set. And now, I put marking lines to indicate it, that it is rising edge triggered. I will have something that shows whether it's rising edge or falling edge. I drew it, I used these to help me space it out, but when I did it on the exam, I just put solid bars that came down from the rising edge to indicate that it was rising edge triggered. The other one I could say instead of for a JK flip-flop, I could say for this device, something like this. For this device, finish the timing diagram. Well, this one has this little bubble at the clock input. That means it's negative edge triggered instead of rising edge triggered, right? And then I could do the waveforms for A and B, and you have to see where they're plugged in and make sure to make that connection. Anyways, other than that, we look and say Q is, we don't know, right? There's no rising edge. If I don't tell you what it is, you don't know. The next thing that happens is the rising edge happens. We see J and not K. J and not K means it sets to 1. Nothing changes until the next rising edge. Now I have K and not J, so it drops. It ignores this, right? Because there's no rising edge. This doesn't matter. It would matter on a latch, but it doesn't matter on a flip-flop. Rising edge, I get 1 and 1. 1 and 1 is toggle. Nothing happens until the next rising edge. I get a K and, oh, well, it is both J and K, so we toggle again. Next rising edge, 1 and 1, toggle again. That's all. Right, this is way easier than what we did, so I will probably have something slightly more difficult that might have like a D and a JK flip-flop, 2 JKs, or even a counter, right? We've done the counters that are connected together, and show me the timing diagram for the counters. I didn't ask, but a good follow-on question to this is if I said, exam questions are harder to write than you think. I want to make sure it makes sense. So assuming that each of these space is 10 nanoseconds, 10, 20, 30, 40. And something like these are centered at 5 nanoseconds past the clock or something. I have to be more detailed, right? And there was a clock to Q delay. Sorry, let me rephrase that. And this device is non-ideal. What potential problems could we see? Right, and it's what I'm looking for is setup and hold time errors there with that question. Remember the setup and hold time. Setup time being the time that is required for it to be the value you want it to be before the rising edge. And hold time is the amount of time that it needs to stay there after the rising edge. Right, just remember that those are errors. There are issues that you might have. I might have something like this, and I might have specified, the diagram would be more clear and wouldn't be as handwritten garbage. And so like this is 10, 20, 30, 40, 50, 60, 70 nanoseconds. And I would say that this is like 68 nanoseconds right here, that transition. What is my minimum? So that'd be another way to ask this. If you had that, and I could ask what is the minimum setup time required for this circuit to function? For this waveform. 2 nanoseconds, yeah. If it's 2 nanoseconds, I just make it and we're fine. Okay, so these next ones I have to pull up the overhead projector, and hopefully it works now because it worked earlier. There we go. Okay. Sorry, I'm trying to remember where I need to go to get my exam because it's on my laptop, but I was having issues connecting the laptop to the projector. It's off for a bit so I don't have to accidentally show you guys my password or something stupid. Last time I did this, it was in the other room and I have the document projector and it's just much easier to do that. Okay, so I can put this back on. So this is now like the real final version of the final exam that I gave last semester. We're just working, come on. Okay, well, while this, there we go, okay. Here's a real question. This says, identify and, let me make sure my zoom is pointed in the right direction. Sorry. Question says, identify and correct the error in the following lines of code using the provided error message. Something like this is likely. I'm going to give you an error message and some code, and I'm going to make you tell me what's wrong with it based on the context of the code and the error message. Take just a minute to look at this and see if you can find the error. There's only one. This one's easy.
Just put an extra Z in there.
Yes, exactly. So it says the hint, right, is that it's in line 58. There's also a line that says 22, but there's no line 22 in this code, so that's kind of not helpful. Line 58, you come down to here. It says, well, data is assigned to this. I'm missing the Z here. There's 7 Z's, and this is 7 down to 0, which means 8 bits, right? That's all. That's the only error I'm looking for. And I didn't actually have this highlighted in the final exam. I don't know why it shows up highlighted in this one. It's really funny. That's the magic of Canvas, is sometimes weird things happen. So anyways, a question like that. And it's important is if you look at all of the code, right, this says model the bus, model the PC, right? What is this code? This is your project. This is project 3, 2 actually. And so that context is how you would know the correct fix is adding a Z, not reducing the width of the accumulator, right? So you would still get, let's see, this is 4 points. You'd still get 2 or 3 of the points, depending how I felt when I wrote the rubric, for changing this to be 6 down to 0 to match the Z's. But contextually, that's not the correct answer. Okay, next one, plenty of time, we're doing okay. This one says, the following questions pertain to the code below, which is incomplete VHDL to detect the sequence 101 on the data port and should detect overlapping sequences, i.e. 10101 should cause DET detect to go high twice. It's a 2-process state machine where one process handles the next state's logic, and the other process updates the current state with the NS on each clock. Okay, so I'll come back to the code in just a minute after I show you guys the questions. And I'm not quite sure how I'm going to do this, but people in video can flash back and forth if you end up rewatching this. But what we're going to do is first ask, is it a Mealy or a Moore state machine? So I'm going to write these questions here so that we have them for reference. Okay, so it says Mealy or Moore. Next question is identify and correct 5 errors. Part C, finish. Oh, more specifically on that, do not include any issue in state S3, just because I haven't written it, you'll see. And there are no errors involving semicolons, returns, data types, or sensitivity lists. There are other kinds of errors. They do include issues with both syntax and functionality. Part C is finish state 3. And part 4 is draw the state diagram. State diagram. A, B, C. Okay, so I said in this question, oh, there's a part E. Oh, part E says you're now required to write a test bench. I don't know if I'll get to that one, but it's okay. So I said it may be useful to do part B first so that you visualize what the state machine is supposed to do. Now, let me, for the sake of Zoom, point this at the whiteboard. Okay, so we're trying to detect 101. I can promise you the sequence will not be 101 on this exam because I've used this example a whole bunch this semester. 101. Now, oh, there is actually one issue first. If we look at the code, we need to decide, is it a mealy or a more first? Because otherwise we're gonna have a hard time writing the state diagram for this, right? Because if it's mealy, we're A, B, C. And if we're a more, it's A, B, C, B. How do I know that? Well, in a mealy state machine for a sequence detector, it takes the same number of states as you have in your sequence. If it's a more, it has one extra. Okay, so let's look at the code. This is not the easiest thing in the world to do with this stupid Zoom. Scroll down. Here you go. It's all of the code. It's a little bit small in the back, but I think it's just readable enough. Is it mealy or more? One for who thinks it's mealy? Who thinks it's more? Okay, most of the class thinks it's more. It is more. How do I know? Well, the big giveaway is the number of states. It takes 4 states, right? It just is. The other giveaway is this detect. This detect says detect equals 1 without any conditionals, right? Because that's the definition of mealy versus more. A more state machine, the output only depends upon which state you're in. That's 3. In a mealy state machine, it depends on both the state you're in and what are the inputs. The detector be inside the if statements. Right? Okay. So we now know that it is a more state machine. So that means I do need 4 states. What I said to do is to draw, right? If you recall, in a sequence detector, always start by just writing the correct path. 1, 0, 1, and let's change this D to be a proper Moore state machine. Detect. Okay, you just got half the points. If you don't do this, you're gonna miss all the points. Make sure they get the path correct. Now, we can go back and start filling in the other options. Well, A is easy because it's just staying put, right? If we don't even start the sequence, don't do it. Now, B is a little bit trickier and people mess this up. So if I do 1 and then I see another, if I see the 0, I go on. What happens if I see the 1 in B? We stay because B is saying I've seen 1, 1. 1, 1, 1, 1, I hang out in B. All right, C says if I get 1, 0, 0, where do I go? Yes, I restart. Okay, now if I do 1, 0, 1, I've got my detect, and I should detect overlapping sequences of 1, 0, 1. So this is a good idea to make sure that this just says detect twice, right? That was what I said. Make sure this happens. So I go 1, 0, 1, now 0.
Go back to C.
I go back to C. Exactly, because I need to be in a point, so when I see another 1, I get detected. All right, so are we complete? What do we need?
The one.
The 1 for D
Just check out D.
goes to B. There you go. So that's the state machine that we're supposed to do. So now that you know what that state machine is supposed to do, remember that part, so we did A, we've done D. Now we're looking for 5 errors. Those 5 errors are, we're not including state 3, is what I said, but they include both functionality and syntax. So any code that doesn't do this is wrong. All right, let's look at that. Okay, let's find 5 errors. Now, as usual, there are actually, I believe, 7 in this one. I try and do a couple more than I asked for because I don't want you guys to get stumped just because you don't see that one specific error, right? I did say, to save you some time, there are no errors with semicolons or sensitivity lists, right? What else did I say? Semicolons returns, which is obviously right. There's no return issue in in VHDL. Data types nor sensitivity lists. So you don't have to worry about converting any data types. And the way I write these, just so you guys know, is I write the code, I build a test bench, make sure it works, and then I go throw 5 things wrong with it. So does anyone see an error?
State 0, you need the else if for 0.
Right. I need an else if. What else do I do? The issue is I don't care. That's the implication. Without the else if is I don't care what happens. That's a problem. Okay, another error. Yes, state 1 doesn't do what it's supposed to do. Right. So state 1, which is B, is if I get a 1, I stay in B. State 1, if I get a 1, I go back to state 0. This is functionally wrong.
Wait, wouldn't it just be an else statement, not else if?
Else or else if.
Okay, they both work.
They will both work. Because so else if will work as a don't, you'll never see the don't care as long as I've covered all possible results. Now, you're kind of correct, right? Because if I get like an X or a Z, well, I don't know. Because that data type is standard logic, so it could be other things. But for 1 or 0, I'm complete. Okay. Yeah. But yeah, if you wrote else, you'd be fine as well. And we have the same kind of issue in S2. The reason is last semester I didn't make as big of a deal about doing the else's as I did this semester, so I didn't worry about that in the code. All right. So state 2. Do we see the error there? Yeah, I'm missing the else on that one as well. Okay. Let's see. I know there's an error. There's a clock error. Can someone find the clock error? What data type is clock? It's not declared. There is no clock. It's an undeclared signal. That's the error. Okay. There is also an error with the first, there is an error in that first process. Yeah. Yeah. Reset is being assigned to 1. That's wrong. There's another error in that process.
To be current state for the next.
Yes. Current state should go to S0, not next state. If I try and assign next state in multiple processes, I'm going to have a bad time. Okay, there we go. That's the general idea of that. I don't know if there might be another error in there, but we found 6, so I think we're satisfied. Okay. Last question is part C is finish S3. Let's write state 3. Make sure it works. And if you look at the question, I'll pop it up real quick. I made it easy for you. I copied the skeleton code there so that you can go fill it out. But for now, let's look at it. What does state 3 do? Well, state 3 is just saying if we get a, oops, I didn't finish this, right? If I see a 1, go to B. If I see the 0, go to C. So it should say if data is 1, go to state B. So we would say next state equals S1. Else if data is 0, next state equals C, which is S2. That, right? Nice and easy, I hope. I'll just show this. We're out of time, but I will show it. It says you are now tasked with creating a test bench for the sequence detector. Use the skeleton code below to finish writing the test bench. The module secgen sequence generator secgen creates a new bit of data on each clock rising edge. Just follow the comments in the code to get full credit. Okay. So the first thing that it says to do is declare the necessary signals using as few signals as possible. What that's really looking to do is for you to build all of the clock data, resets, detect signals, right? And the signals that connect those two together. Then you're going to generate a clock signal of 1 megahertz. You can do this through the process method that we've used before, or you can use the clock equals not clock method that I've shown as well. Then I ask you to write the instantiations for both sequence detect and sequence generator. So you know what sequence detect does. I've described what sequence generator does. So as long as you wire the output of the sec into the input of data, you're right. That's like the big thing, right? It's just wiring those two together in the correct method. I could ask something like, instead of that, I could say like, draw me the block diagram of this system, right? I could ask for that kind of thing. Just like I could ask you, draw me the complete block diagram of the microprocessor, including blah, blah, blah. But then that's really all. So I could also ask, and I like this question as we're running out of time, what source of error would we see if we tried to implement this on a real FPGA that wouldn't show up in the test bench? Yes, delay. So the clock is both asserting new data for the sequence generator and trying to clock it in at the same time. If there is a difference in delay path, or what we call clock jitter, right? If there's real world problems in this, we don't know what we're getting generated. There's a race condition. There's a real error there. Okay, that was the final exam from last semester. It'll look something like that. I will warn you that if you go back and look at the first exam, there was the questions that actually use little MOS devices, right? The NMOS and PMOS, and asks you to build the pull-up network or the pull-down network. Go back and look at those, that you could see one of those. What will definitely be on the exam that wasn't in this review is the state machine design question that has you do the state diagram, the state table, the K-map, and then the circuits. That will be on there. And it wasn't in here. And a likely one, because you guys have struggled with it, that could show up is the parallel load for counters and shift registers and that kind of thing. Parallel loading. The other last one that would be a callback to the early is just doing some Boolean logic simplification. That one would be like one question. It wouldn't be super difficult. If you don't review it and missed it, you'd probably survive the exam. Okay. I'll be around. Good luck on your microprocessor project. I should be in my office hours for the next little while. This afternoon, I'm going to be in senior design reviews all from 1:30 until 5 or something. So I won't be available then, unfortunately. But if you send me emails, I will answer questions, and I will try and be available on Friday for like Zoom meetings. If you guys have any other Project 3 questions. We have no lab on Monday, because again, I will be in senior project design reviews all day. So this department, we don't do labs last week class, so no lab Monday. Good luck, send me emails for questions and we'll try and set up Zoom time if you need more help than that. Good luck, guys.